So we worked through all of these things, polynomial division and the remainder theorem. So now we need to move on to the factor theorem. The factor theorem says two things, but basically they are one and the same. The first thing says if f of c equals 0, then x minus c is a factor. The second thing says the exact same thing but in reverse order. If x minus c is a factor, then f of c is equal a 0. So the purpose of this factor theorem is to determine the relationship between our actual value and the factors that go with it. So if c is a 0 of a function, then our factor associated with it is x minus c. And that's exactly what option 2 says, but in reverse order. If x minus c is a factor of a function, then that tells us that our c value is a 0 of the function. Now, we have actually utilized this quite a bit. We just didn't give a name to this process. So let me show you what I mean. If we have the equation x squared plus x minus 6 equals 0, we know we could solve it by using the factoring method. So this factors as x plus 3 and x minus 2. After we factor it, we just set each of our factors equal to 0. And so that gives me the first solution of x equals negative 3. And that gives me the second solution of x equals 2. So the second part of the factor theorem says, if these two things here are factors of my polynomials, then these are zeros of my polynomials. And that's something that we've used quite often. Part 1 says the vice versa. It says, if this is a 0 of my function, then this is a factor of my function, x minus my 0. Same thing with the opposite one. If negative 3 is a 0 of my function, the factor is x minus a negative 3. But if I were to simplify that, that would give me x plus 3, which is the factor that I have here. So the relationship between these is if this is a 0, you subtract it from x, and that gives you your factor. Or if you have the factor, then you set it equal to 0, and that gives you your 0. Okay, so let's actually do an example that utilizes this. We have a function here, f of x equals 3x to the third plus 25x squared plus 42x minus 40. And in essence, what we want to do here is we want to factor it. So if we want to try and factor this here, we might try and factor it using the techniques that we learned back in Chapter R. So if we did 3x cubed plus 25x squared plus 42x minus 40, we know that it has 4 terms. So our original thought process is let's factor it by grouping. Let me group my first 2 and my last 2 terms. So if I were to pull out a common factor of my first 2 terms, that would leave me with 3x plus 25. Then a common factor in my back 2 terms would just be 2, and so that leaves me with 21x minus 20. Now the problem with this is for our factor by grouping technique to work, our parentheses have to match. Those have to become a common factor so we can factor them out. So those don't match. So what happens here when this doesn't work out? Well, that's when we get to utilize all the other things that we've done so far in this section. So if we can no longer factor it by using our old school techniques, then we now need to factor it by using long division, or I prefer synthetic division. And in this example, it's a little bit easier because they give us what to start out with, what to divide it by. So that's what we're going to do here. We're going to factor it, and then after we factor it, we move on to part B, and we find the zeros of the function. Or another way that it could word it is we can solve the equation when it's set equal to 0. Let's go ahead and start back from the beginning. We want to factor it by using synthetic division. So I need to set it up. Ask yourself if you're missing any terms. If so, you need to put in zeros for those terms. If not, then you just need to use your coefficients. 3, 25, 42, negative 40. And we get to divide it by the value that they gave us, negative 5. So we run through our synthetic division. Bring down my first digit, multiply, add, 25 minus 15 gives me 10. 10 times negative 5 gives me negative 50. 42 minus 50 gives me negative 8. Negative 8 times negative 5 gives me 40. Negative 40 plus 40 gives us a remainder of 0. Now, we know that we absolutely should come up with a 0 here because it guaranteed us that we should. If negative 5 is a 0, that tells us that our remainder then should be 0. So if it tells you something's a 0 and you didn't get 0 as a remainder, that means you made a mistake here. Okay, what we did now was we factored this. So I'm going to put this in the division algorithm method. We have our original polynomial, 3x cubed plus 25x squared plus 42x minus 40. And I'm going to set this up as my divisor, what I divided by, times my quotient plus my remainder. Okay, my divisor might be a little bit difficult to see. I'll talk about that in a minute. The quotient is our answer right here. All we need to do is we need to put our x values back in. We started with a cubed value, so I need to go 1 degree less. So this gives me 3x squared, and then a 10x, and then my constant term. And I go ahead and put in my addition symbol if need be. So my quotient here is 3x squared plus x minus 8. Now my remainder came out to be 0, so I really could put in a plus 0 in this problem, but we know that we always want to leave things as simplified as possible, so why put that in there when we in essence don't need it? All right, now what about my divisor? This is where the factor theorem comes into play. I know that my negative 5 is a 0 of my function because I confirmed it by doing the work here, and it told us that at the beginning. So what's our divisor, or what's our factor that goes with it? So the factor theorem says, if f of c equals 0, then our factor is x minus c. Well, if negative 5 is a 0, then our factor is x minus a negative 5. Or if I simplify that, that becomes x plus 5, and so that's what my divisor is. That's how I go from a divisor to a factor. All right, so we've done some of this problem. Our goal was to factor this polynomial completely using that negative 5 as a 0. We factored it by one step. We took it from a degree 3 problem down to a degree 2 problem times degree 1. But we want to factor this completely. So I want to see if I can factor this using our old school techniques that we learned back in chapter R. I don't need to do anything with my x plus 5. It is factored as far as possible, but this here is a trinomial in descending order. So let me factor it by using my trinomial or my unfoil process. So first I have 3x times x to give me 3x squared. I have 4 times 2 to give me 8. Outside gives me a 6x. Inside gives me a 4x. If I'm looking for a positive 10x, at first glance that might seem like it worked out. I just make them both positive. But that doesn't work out because I know this last sign here has to be negative, and a positive 4 times a positive 2 does not give me a negative 8. So that isn't the way we go. Let's try again. Again, keeping my x plus 5, and then keeping my 3x times x, but let me switch my 2 and my 4. My outside is a 12x. My inside is a 2x. If I still want my positive 10x, I can take that as a positive 12 minus 2, and that does give me my negative 8 back here. So in part A, if we want to factor this completely, now we have it. We are down to linear or degree 1 pieces in all of this. So this is my answer to part A. Now we get to use this to find the zeros of the polynomial. Or another way that it might be worded is to solve the equation where my polynomial was set equal to 0. Well, if I wanted to do that, then all I needed to do was to set each one of these steps equal to 0. If I set my polynomial equal to 0, then that sets this factored step equal to 0, then that sets this factored step equal to 0. So if I want to find the zeros of the function, then I just need to set each one of these factors equal to 0. So in part B, I take x plus 5 equal it to 0, gives me the solution of x equals negative 5. 3x minus 2, set it equal to 0, gives me the solution of x equals 2/3. And x plus 4 equals 0, it gives me the solution of x equals negative 4. Now, I want to confirm that I at least have the correct number of answers, and I do that by looking at the degree. This was a degree 3 problem, so I should have 3 answers, and I do. Negative 5, 2/3, and negative 4. So I can at least confirm that I have the correct number of answers. There's a couple of ways to fully check this to make sure that my answers are what they're supposed to be. If I'm looking for when my polynomial is set equal to 0, all I can do to check these is to substitute these back in and confirm that they are equal to 0. Now we can do that using the old way of just substituting them in and simplifying, or we now know that we can do that by using synthetic division. A different way that you can check these is by thinking about what we actually did. If we want the zeros of the function, what does that mean on our graph? We know that zeros really means the exact same thing as x-intercepts on our graph. So let's use our graphing calculator to check this here. Let me substitute in my equation, which was 3x to the third plus 25x squared plus 42x minus 40. Graphing it on our standard window. Now, I don't see my entire graph, but I see what I'm looking for. I'm looking for the zeros of this function. In essence, I'm looking for my x-intercepts. I see 3 x-intercepts. We just need to confirm that those are what we came up with. We came up with the answers of negative 5, negative 4, and 2/3. At first glance, those look like they do match. If you want to check it even further, we can do that by doing the trace button and substituting in our x values. Confirm that negative 5 works. It does because our y value is 0. Confirm that negative 4 works. It does because our y value is 0. And confirm that 2/3 work. And it does because our y value is 0. So our graph, or our x-intercepts, confirms that we do have our correct answers here. So this basically puts all the pieces of the puzzle together. What do we do when we can't factor it by using the techniques that we learned back in Chapter R? We're going to do synthetic division. If we give us a 0, how does that transform into factor notation? We just take x minus that 0, continue to factor, set each of your factors equal to 0, and that gives you all the solutions or all the zeros of your function. And so now we should be able to solve almost any type of equation, even if it doesn't factor.